the previous lecture, I had introduced you to the most common faults in rotating machines, and in this lecture I am going to focus on how unbalance can be detected in rotating machines. Okay. So, what do I mean by unbalance? Okay. Suppose I have a shaft and the shaft could be carrying a pulley, a gear, and if you look at this view here, suppose there is an unbalanced mass here. So, each time this unit is rotating, okay, I will have a radial force m e omega square r, which is going to come along the periphery. Okay. So, if the initial shaft load was W, obviously at the bearings, both the bearings which are getting supported, I will have a reaction W by 2, W by 2 if they are equidistant, maybe A, B, L. So, A is equal to B is equal to L by 2, and this is the radial distance from the center line. M is the unbalanced mass, omega is the speed of rotation. So, I have such a scenario which can happen, and this could be maybe a set of blades in an impeller or a fan. Okay. So, in many industrial scenario, you will come across such units, maybe an ID fan, induced draft fan, or an FD fan, etc. Okay. Either to induce in air into the system or expel the exhaust gases from a combustion operation, etc. I will give an example. For example, in an FD fan, we have the combustion gases. Suppose it was coal combustion, there will be a lot of fly ash in this gas. So, this fly ash, because of the ambient moisture, it can so happen with time these ashes may get deposited, and the quantity is so large that it creates a substantial amount of radial force. So, what is going to happen is this is going to load the system, and then what happens if the shaft is not designed to carry such an excessive load, it may fail. The bearings, because they are running for a certain life, the extra load which comes because of the unbalanced mass is going to reduce the dynamic load capacity of the bearing. So, bearings will fail at a time which is much less than the life of the bearing. So, all these scenarios happen. So, and then of course, one leads to the another in machinery condition monitoring. If an unbalance was let to grow undetected, what is going to happen is this will lead to a bearing failure, and then you will be investigating a bearing failure without actually going into the failure because of this unbalance. So, these are some of the scenarios. If you go into a production plant of where they make milk powder, or you have an agitator or a mixing tank, some mixing tank, and you have a large fan. which is rotating, supported on bearings, and there is some liquid here. What happens if something gets stuck here? The loads will come and there will be wobbling, etc. So, one will lead to the another. Okay. Such kind of faults occur, and if I was to classify this, one is known as static unbalance and other is known as the dynamic unbalance. For example, if the shaft is very small and I have just a significant force in the radial plane, this is a good example of a static unbalance. So, it is unbalanced in one plane, as opposed to think of a large turbine in a power plant. I have a long shaft where there are stacks of blades. And maybe these are all stacks of blade. Later on I will show you photographs of gas turbines, where you will see how closely these blades are there. And so, unbalance here in any plane is going to give rise to a couple, it is going to give rise to a moment. So, if I put an unbalanced mass here, this also will give rise to a radial moment. So, this has to be done what is known as the multi-plane balancing. Okay. And those of you who have done balancing on multi-cylinder long engines or multi-plane turbines, you can do it by such methods, but this will give rise to moments as opposed to this giving rise to reaction forces at the bearing locations. And we will particularly focus on small machines where we are talking about static unbalance. The question is, in the first place, why did this unbalance occur? It could be poor casting. Imagine a pulley which is mounted on a shaft. If there are blowholes, because pulleys are usually cast, so blowholes during casting. For once or twice an operation, this is okay, but with a lot of with time, these forces will induce stresses in these, okay, and they are having a little problem. Okay. Installation issues, centering, because if I have a shaft which is supported on bearings, I have exaggerated this. So, this is my shaft center, and because of uneven clearances, I have what is known as the centering issues. And particularly this happens when they install large machines where the shafts of the two machines have to meet. Okay. And this because of incorrect centering, these issues could be happen. So, I have a mass which is not in center, okay, and this will give rise to another. And of course, the other one is the operational maintenance issues, like I was saying, the fly ash deposits in the FD fan or the milk powder deposit in a food processing plant, etc. So, these are the reasons why unbalance occur in shaft. We cannot avoid it, but with a good periodic inspection of the unit, we might as well reduce it. So, if a shaft is rotating, okay, there will be some amount of unbalanced mass per unit weight of the shaft and as a function of speed, and this is given by this residual unbalance as per ISO 1940/1973. There are grades of balancing, 0Z4 being very precision, and you will see these are for very high speed machines. The tolerances are very low, and for slowly moving machines I can have a little higher grade of unbalance left. because it is all function of omega square. So, you will see this surface finish does matter for high speed machines. Now, we are talking about cryo engines running at 70,000 rpm, 80,000 rpm. These are very difficult rotors to balance, to machine. So, you can understand the tolerances. So, I will give you a list of the balancing quality grades which are as per the ISO standard. If you look at here 0.4, spindles, discs and armatures of precision grinders and gyroscopes, G1 for tape recorders. Okay, these are for G2.5 for gas and steam turbines. Gas and steam turbines, usually steam turbines around 5,000, gas turbines around 30,000 rpm, as opposed to G4000, a slowly moving marine diesel engine. Okay, this could be maybe 500 rpm. So, you can see once the speed increases, your balancing grade has to improve. Okay. I will just give you an example, maybe in some of the later classes I will show you the pictures. See, if you go to a paper mill, okay, there are many rolls. This could be 100 such rolls, okay, and this is a there are other processes here, a press section, and these are nothing but the dryer rolls which are steam heated in the inside, and then the paper, which I am drawing a black line here, go out. Now, if you think of each of these rolls are the order of, this is about 4 meter long, and this diameter could be about half a meter. Imagine this paper which I am denoting as here. Imagine if these rolls, long rolls, had unbalance, what is going to happen? You will not get, and you have a similar roll on the top as well. And the paper, which is actually a wet pulp at the beginning, and then because of the stream drying roll, and there could be such hundreds of such rolls in a paper mill. If there was an unbalance, what is going to happen? The forces would be uneven. So, I will not get a flat paper, but I will get a paper with non-uniform thickness. So, the quality would deteriorate. Same is true for even rolling mills. In steel plants. So, the product quality gets influenced by the amount of unbalance in all these rolls. So, the question is, how do we detect such unbalance? So, what is the characteristic of the unbalance by vibration monitoring? So, if I was to take a shaft supported on bearings, I will because of, so you see this is my axial direction and this is the radial plane where I have the horizontal and then this is the vertical. So, this is the radial plane and things are rotating at 1x. By 1x I mean the rotational speed of the shaft. So, when it is 2x, it means 2 times, 3x, 3 times and so on. So, this is an unbalance, this is rotating. So, I will have a force m e omega square r. So, this is nothing but a harmonic force, because it is rotating along with the speed. So, it is, as opposed to vibration in the axial direction, it is more in the radial direction. So, I will have, this is for rotors between bearings, short rotors, a strong radial vibrations. If you look at the magnitude in either in V and H are the much higher compared to axial, and usually because if this is a balanced system, V and H will be of the same order of magnitude and equal to the same. And obviously, this will increase with rotor speed as square in phase between the support bearings. For example, if I measure the vibration here with a transducer and vibration here with the transducer, because of unbalance, if I measure, so this is signal x, signal y, if I measure the phase between x and y, I should get them to be 0 degree or close to 0 degree, because they are in phase, means when it is a maximum here, it is also a maximum here. Okay. And when it is a minimum here, it is a minimum here. So, vibrations is in phase. By the way, just to recollect, how do I calculate the vibrations phase between two sensors x and y? So, I know x t is the measured vibrations. If I do an FFT, just to recollect, I will get the Fourier spectrum of x t as x f, similarly for y t. I will get y f. So, I have to do them simultaneously. So, the transfer function x h x y is nothing but s x y f by s x x frequency. Okay. And this transfer function will have a magnitude and the phase part phi x y. So, phi x y is nothing but tan inverse imaginary part of h x y f by real part of h x y f. These are all functions of frequency. Okay. And particularly at the rotate, because this is rotating at a particular frequency, the forcing frequency is nothing but n by 60 hertz. Okay. And what is, how is the relation to omega? Omega is nothing but 2 pi f, where n is in RPM. So, n omega in radians per second or f in hertz, they are all related, and the forcing function is the external force which is occurring at a frequency. Omega is responsible for this vibrations x and y on the bearing. So, the characteristics of unbalance in a rotor in between bearings is strong 1x radial vibrations, vibration is strongly harmonic, magnitude of vibration increases with rotor speed, and vibrations in phase between the support bearings. And these can be estimated or calculated or measured by a dual channel signal analyzer or an FFT analyzer. Okay. Now, this is just to give you an example where we have measured the cross spectrum between two signals, and you will see the phase angle is only 13.149 degrees. This is subject to other unbalances in the system. So, with the frequency of 24 hertz, that is the rotational speed in hertz, I can measure the magnitude and so on. These are case of in phase vibrations. But when there is an overhang rotor, supported on bearings, and I have a disc put here which is at an overhang, and there is an unbalanced mass. Okay. There could be a strong axial along with the radial. So, in the radial plane, I will have H, I will have V. And then axial vibrations may be unsteady because it may not be uniform, and axial phase may be unsteady. If you measure the phase angle between them, this can happen. So, these are some of the scenarios which can happen in machinery condition monitoring. As opposed to shaft being unbalanced, there could be a scenario where the shaft is bent. This is my original shaft, but it has bend or bowed. Okay. These are the bearings, bent or bowed shaft. So, a bent shaft has distinct second harmonic. That means I will have a strong 2x component. Okay. And this can be easily measured by a coast up. By coast up, I mean I am ramping up the speed, and which you can see in what is known as an waterfall diagram. Okay. Now, the problem with condition based monitoring, condition monitoring is the original source could be a bent shaft or a unbalanced, but the effect is actually felt in the bearings. And why it is felt in the bearings is something I will explain to you now. Imagine a bearing. Those of you had a course in machine design will know a bearing. Okay, I have see, this is my outer race, this is my inner race, and this is my rolling element, which could be a ball or a roller. What happens, because these are all very hard, nice surfaces, we have a lot of lubricant, a layer of course, there is a retainer which I have not drawn, layer of lubricant. Now, what happens if this force increases, some force. Now, what is the origin of this force? It is the reactions which have increased at the supports because of unbalance. So, this force increases, the normal forces increases, the frictional force is nothing but mu times n. So, the frictional force will increase. Okay. So, what does the frictional force increase? So, what is going to happen? Because it is going to rub against the surfaces, the temperature would rise. Okay. If temperature rises, a lot of heat generation because of frictional forces, the lubricant could get baked. If the lubricant gets baked, and lubricant is a chemical fluid, I mean. So, if the lubricant will burn and the burnt particles will become hard hydrocarbon residues, and they are very hard. So, imagine in your rolling element bearings, because of an unbalanced force, the temperature rose, nobody noticed it. The lubricant baked, nobody noticed it. Lubricant became hard impurities. And then what has happened? Imagine you are going on a surface where there are a lot of rocks on the road. Obviously, you are going to have wear and tear. So, the bearing is going to have, bearing surfaces will get scored, spalled, and then there will be a lot of pits in the races. And imagine what would happen, the bearing would suddenly fail. So, what has happened is a defect in a rolling element bearing is being noticed because of this force which was not noticed by the operator. So, this is the common scenario I have seen. I get calls, people say we have a bearing failure. When I look at the past data, I see the bearing failed because of an unbalanced force, because nobody took this into account. So, these are some of the scenarios one has to be very careful when we attack problems in the real world. So, undesirable effects of the unbalance, excessive loads at support bearings, increase in the fatigue loads on the rotor, I just told you, leads to problem like bearing faults, rotor stator rubs, loose foundations. So, these are all scenarios, because foundations will become loose because periodically there is a force which is hitting on the bearings. Okay. So, more of these we will discuss in the subsequent class, how to actually, if a unbalance has occurred, how to fix it, and that is the methods of balancing, which I will discuss in the next lecture. Thank you.